Hi, everybody. A very good morning. So we have 7 of you. Okay, maybe we'll just wait for 1 more minute so that your friends will join and then we can start right away. Okay, seems like nobody is joining. Fine, let me share my screen. All right, so we started with thermodynamics last class, right? So we saw some basic things. What is system, what is surrounding, what are the different types of system we can have: closed system, open system, isolated system, adiabatic systems, right? And then we saw what are the things that used to be, which are used for description of a system, right? Those are what are called as variables of properties, intensive properties, extensive properties, right? What are intensive properties? Which are independent of the amount of substance. When you change the amount, that particular property will not change. Whereas extensive properties are the ones which you, when you change the amount, the property will change, right? Examples: volume, number of moles, energy. You can even take that any energy, that is heat, right? All these can be examples, right? And examples for intensive property: temperature, pressure, right? Or density. All these things can be examples, right? And there is another way of classifying these properties. And I told you, okay, there's another thing for 100% description. If you want to know anything and everything about the system, all we need is only three things: two intensive properties and one number of moles. Okay, but every time intensive properties might not be given to us, right? So there'll sometimes you'll be given extensive properties, but you'll be able to convert extensive properties into intensive property if you divide the extensive property with the number of moles. For example, energy is an extensive property. If you divide by the number of moles, you're going to get molar energy. Joule per mole is what you will get. Same goes with volume: normal volume, molar volume if you divide number of moles. Another way is that if you divide two extensive properties, again, you're going to get intensive properties. Say, for example, mass, volume, you divide, both are extensive properties, you're going to get intensive property, that is density, right? Okay. Then we went on to see another way by which we'll be able to classify these variables or functions or properties, right? So we can have something called as state variables or state functions, or path variables or path functions, right? So when I say state, I'm talking about conditions. What is the conditions on which the system is present, right? So in case of state variables, it doesn't matter how we reach from state 1 to state 2. All that matters is what is the initial state, what is the final state. How I reached doesn't matter, right? Those are what are called the state functions. And path functions obviously are going to depend upon the path. They're going to depend on the initial and final state, as well as how you reach from the path state 1 to state 2. That also matters for path functions. Example is Q, that is heat, work done, energy, right? And other things: number of moles, pressure, volume, temperature. All these are state variables or state functions, right? And then we went on to see what is the relationship between heat and temperature. Okay, you saw that there was a relationship. We said that the Q is directly proportional to delta T. That means the heat will flow, right? Heat will flow if there is difference in temperature. Is it not, right? So you understand, for example, if at all I have two bodies in contact, one is at 25 degrees Celsius, another at 100 degrees Celsius, right? Definitely you'll understand that the heat is going to flow from here to here, from the higher temperature to the lower temperature. But say if both of them are at 25 degrees Celsius and 25 degrees Celsius, obviously there is no heat flow from this side to this side or from this side to this side. Okay, so we understand that there should be some difference in temperature for the heat to flow between two different bodies, or from system to surrounding. System should be at higher temperature, or the surrounding should be at lower temperature, or vice versa. Only if there is a difference then you can have heat flow. And that's why we say that Q is directly proportional to delta T. Change in temperature if you have, then only the heat flow can happen, Q. Right? So to remove the proportionality sign, we introduce a constant C, and that is what is called as heat capacity or specific heat capacity. Right? And then we can have two modifications done to the equation. One, because Q is an extensive property, that means it is going to depend upon the amount. Right? So in order to accommodate that, we introduce mass. Right? In that case, the C will be called as mass heat capacity or mass specific heat capacity. Now, if at all you include N, that is number of moles, Q is equal to NC del T. In that case, it is going to be called as molar specific heat capacity or molar heat capacity. And we saw the definitions also. What are the definitions? For Cm, that is mass heat capacity, and for Cn, that is molar heat capacity. All right. Okay, people. Now, there is another way by which you'll be able to talk about this particular heat capacity, depending on what kind of conditions you're going to do. You're going to make the measurement, right? At what kind of conditions you're talking about these kind of processes, right? You'll be able to have two different things. Right. So this heat cap. Okay. Before we move on to that, let us talk about the unit. Right. Let us talk about the unit of Cm and Cn. Right. So you understand that Cm will have a unit. Right. This is, I know, is joules. I know this is going to be in grams. Right. And this is going to be in Kelvin. Okay. So can I write it is going to be joule per gram, or it should be kilograms actually, not grams. SI unit, if you write it is kilograms. Right. So we will be able to write the unit of Cm, that is mass heat capacity, as joule per kg per Kelvin. That is the unit. Right. And in this case, if you check, this is moles, this is joules, and this is in Kelvin. Right. So Cn will have a unit of joule per mole per Kelvin. That is the unit of this thing. What is that? Cn, molar heat capacity. Okay, right, fine. Now moving on, people, as I told you, depending on at what conditions you're going to do the measurements, you will be able to have two different heat capacities. Okay, so this C, either it's Cn or Cm, doesn't matter. Okay, whatever be the molar heat capacity, whether it is in terms of mass or number of moles, they can be of two types. Okay, in general, I can write just C. Okay, now this C, if you're going to do the process under constant volume conditions, that means you're going to do it under vessel which cannot expand, and closed vessel like this. Okay, so that particular heat capacity which you get at constant volume is what is called as CV. So we can write this as heat capacity at constant volume. Okay, and you have something called as CP, and this is going to be heat capacity at constant pressure. If you're going to do the process under constant pressure conditions, the pressure is not changing, then that particular heat capacity which you're going to measure is what is called as heat capacity at constant volume, constant pressure, or just CP, C subscript P. Okay. Right, and there is a relationship between CP and CV that you will be deriving in your physics part, right? But I can directly give you CP minus CV is equal to R. Okay, this R is a universal gas constant. Okay, the CP minus CV is always going to be equal to R, and this is what is called as your Mayer's relationship. Right, and you will have a derivation for this in your physics, right? Again, in thermodynamics, the exact name of the chapter is thermodynamics, that is chemical thermodynamics. What we study here, that is in physics, right? So you will have a derivation for this in your physics. You'll study about this. CP minus CV is equal to R, and it is very, very important to remember this relationship. Okay, so if you know one of them, the other one can be easily calculated. Okay, right. So moving on, so that is about the different heat capacities you can have, CV, CP, how is the relationship between them, all those is already okay, right? Okay, so the next one is, right, so this C, or in general heat capacity, right, is actually directly proportional to the atomicity of the gas. See, in this chapter, we are not going to deal with solids and liquids, okay? Majoritarily, we'll be dealing only with gases. Okay, remember that. So what I'm trying to say is this C is directly proportional to the atomicity of the gases, right? In the sense that if I just say I have helium, right? And say I have H2 and say I have carbon dioxide, right? I have three different gases. This is monoatomic, right? This is diatomic, and I know this is polyatomic, right? So more and more is the atomicity of the gas molecules, more and more will be the C value. So CO2 will have a higher C value than your H2, than your He. Okay, right? Now keeping this in mind, right? Why is it like this? We'll try to understand, right? Why is it like this? We'll try to understand. So what you have to understand is, people, when you have monoatomic gases, right? When you have monoatomic gases, they will have only translatory motion possible, right? Please understand, for any kind of species you have something called as degrees of freedom, right? What are the possible ways it will be able to move, right? So when you have monoatomic gas, say a monoatom like this, obviously there is no question of rotation of this thing. It can move only in straight lines like this. Okay, so monoatomic gases can have only translatory motion. Okay, monoatomic gas can have only translatory motion. Okay, and when you go for a diatomic gas, they can have translatory motion, right? And also they can have a rotatory motion. Okay, they can have translatory motion plus rotatory motion, right? And if you go for any atom which is any gas which is polyatomic, they can have all three types of motion, that is translatory motion, right, rotatory motion, and also you can have vibratory motion, right? You know what is rotation? Rotation is going around in circles, right? Translation is moving in straight line. Vibration means the molecule is there, it is going to vibrate like this. Okay, there are different modes of vibration. Okay, there are different modes: scissoring, rocking, all these things are there. That is too much for your level. If you're interested, please learn about it. What are the different ways of vibratory motion? We don't have to go into the details. Okay, so what you have to understand is monoatomic gases will have only translatory, diatomic gases will have translatory and rotational motion, right? And polyatomic gases will have translatory, rotational, and as well as vibratory motion. There are only three types of motions possible: straight line motion, rotation, or vibration. Only three things are possible. Okay, right. So what we need to understand is this C, there's another way of looking into it. This C is directly proportional to the amount of motions I can have in the molecule, right? This C is directly proportional to the amount of motions I can have in the molecule. So this and this are connected now. Is it not, people? Because when I have only monoatomic gas, I have only one type of motion, translatory. When I go for higher atomicities, higher number of motions are coming. So obviously the C value will also be higher. Okay, right. So now there is another thing which you actually wanted to remember is that, so now please understand, you will see that the temperature will change, right? If you will see that the temperature will change only if the amount of translatory motion changes, right? Only if the amount of translatory motion changes, right? So temperature has no relationship with vibratory motions or rotational motions, right? Temperature has no relationship, like whether you give some amount of heat, right? I mean, whether you if at all the amount of vibration changes or amount of rotation changes, you will understand that temperature has no role to play, right? But if translatory motion changes, right, definitely that will have a great increase in temperature. Okay, right. Now let us look into this. Okay, say I have a gas, right? I have a gas which is having, well, let me take helium for that matter. It has only translatory motion, right? It has only translatory motion, and let us compare it with H2 and CO2 for that matter, which is going to have three different types of motion. I mean, here it is going to have only two, right? Translation and rotation only is possible, right? And CO2 is going to have all the three: translatory, vibration, and rotational motion. Here I am going to have translation motion and only rotational motion. Okay, right. So people, if I start heating the gas, right? If I start heating the gas, right, what is happening? So the molecule will gain more kinetic energy, isn't it? That particular heat energy will be absorbed by the gas molecules and they will try to move faster. All right. So for example, say I give 10 joules of heat to helium, 10 joules of heat to hydrogen, and 10 joules of heat to your carbon dioxide. Okay, right. Now I'm just giving you some random values, people. You will see that the temperature rise around 10 degrees Celsius. This is not exact. I'm just giving you some random values. Okay. So I am seeing that the temperature rises 10 degrees Celsius. Right. Initially, whatever was the temperature, now it is increased by 10 degrees Celsius because I'm heating it. Okay. Now, same 10 joules of heat I'm taking for hydrogen gas, you will see that the temperature rises only 8 degrees Celsius. Okay. And for carbon dioxide, same 10 joules of heat is given, but in this case, the temperature rises only by 6 degrees Celsius. Okay. Now, why is it happening like this? You have to come back to this point, right? Change in translatory motion will only increase the temperature. If the amount of translatory motion increases, then only the temperature increases, right? So what you're understanding here is that the entire 10 joules given to the helium is exactly used in increasing the translatory motion only. Only translatory motion, entire 10 joules is used up for increasing the translatory motion only, right? So fine, that is understood. Now, when I go for hydrogen, right, 10 joules of energy is given, some amount of it will be used for increasing the translation energy, some amount of energy will be used for increasing the rotational energy. Okay, but this rotational energy and temperature has no relationship, right? There'll be, so if you check, if the amount of translatory motion, how much it increases here, and the amount of translatory motion, how much it increases here, it is a very, very, very high value, right? In this case, this is going to be only smaller increase in translatory motion because some amount of heat energy is given to rotational motion also. Is it not? Right? So that is the reason why you are seeing that the temperature rise is very, very high because the entire energy is used for increasing the translation motion. But in the case of hydrogen, you are seeing that the translation motion is increasing as well as rotational motion is increasing. So some amount of energy is given for translation, some amount of energy is given for rotational, and only translation motion increases will give rise to this particular temperature increase. I hope that makes sense to you. And at last, when you go for CO2, right, some amount of energy is given for translation increase, some amount of energy is given for vibrational increase, and some amount of energy is given for rotational increase. And again, these two has no role to play with temperature. Only increase in this will increase the temperature, right? Very less amount of energy is going to increase, it will be used up in increasing the translation energy. That is why you're seeing that very less temperature rise is going to happen when compared to monatomic gas, diatomic gas with respect to a polyatomic gas. Okay, I hope this makes a lot of sense to you. Okay, right. So people, I know that helium is going to have the least of all heat capacities, and hydrogen is going to have, tell me.
Sorry, I'm late, sir. I had internet connections. What is we doing as of now?
Yeah, we are studying about this. What is that? Heat capacities. Okay, we are checking for different gases. If I have polyatomic, monatomic, diatomic gases, how will they have? What is the heat capacity of different monatomic or diatomic gases or polyatomic?
All right, sir.
gases.
Yeah. Also, I've been marked absent.
Yeah, no issues. You can just message your coordinator, whoever is coordinating to you.
Okay, yeah.
And he'll be directly.
All right, sir. Yeah.
Okay. Cool, right? So we understood that why is there a high increase for the same amount of energy given to different gases. We understand that depending on the atomicity of the gas, the temperature rise will be accordingly to that. Right? That we are very able to easily understand. Okay, right. And if I talk in terms of heat capacities, right? I know if I talk in terms of heat capacities, helium will have lesser heat capacity than H2, which is going to have lesser heat capacity than CO2. Right, that we already know because I told you C is directly proportional to the atomicity of the gas. Right, monatomic gases will have lesser than your diatomic gases than your polyatomic gases. Polyatomic gases will have very high heat capacities. Okay, right. So people, I will be able to tell you one more point, and you'll be able to connect this very easily. The heat capacity, right, is inversely proportional to the heat conductivity. Or I can even tell it as heat sensitivity. Right? Now, how am I saying this? Now, look at this, people. I am giving 10 joules of heat to helium, and I'm seeing a 10 degrees Celsius rise. And in the case of hydrogen, only 8 degrees Celsius rise is there for the same 10 joules of energy. right? So can I tell helium is a better conductor of heat than your hydrogen gas? Same way, CO2 is actually a better conductor of heat than your hydrogen gas, than your, sorry. CO2 is, no. H2 is a better conductor of heat than CO2 gas, right? And helium is a better conductor of heat than H2 gas. Because for a small, the amount of energy is given that is entirely used up for increasing the temperature. Obviously, more and more temperature rises for the amount of heat energy, because we are saying that it is going to become a better and better conductor. That is easily understood. Okay, so this point is also understood. Heat capacity is inversely related to the heat conductivity or heat sensitivity of the particle molecule. Higher the heat capacity, lesser and lesser will be the heat conductivity. You can understand. Say if I ask you arrange H2, helium, and CO2 in the order of their heat conductivities, right? You can easily say that H2 is the best conductor than H2 than CO2. We can say this. Okay, we also understood why. Why is it that it's like this? Because we understand that H2 is only going to be monatomic, only translatory motion is there. So whatever energy given to it will be used up for increasing the translatory motion. Very, very simple. And other things are going to follow accordingly. Right? Okay, fine. So people, for a monoatomic gas, directly I'm going to give you the formulas for this thing, how heat and your this thing are related. I'm sorry, what are the CV and CP values for all the monatomic, diatomic, and triatomic gases, like polyatomic gases. Okay, so people, when you have a monoatomic gas, right? When you have a monoatomic gas, remember that the CV value is equal to 3/2 into R into T. There is a derivation for this, okay, but you don't have to worry about it. Okay, any monatomic gas will have a CV value of 3/2 RT, and obviously CP value you know, because you know CP minus CV is equal to R, Mayer's relationship, you know that. Okay, so monatomic gas will have CV value of 3/2 RT. Okay, right? And then for a diatomic gas, why is it changing like this? Okay, for a diatomic gas, right? They will have, I think, 5/2 into R into T. Okay, for a diatomic gas, it is going to be, is it correct? 3/2 RT, this is okay. What about diatomic gases? Diatomic gases will have 5/2 RT only. Okay, fine. Let me check this. No issues. That is not a big deal. And this is not even in a syllabus. Okay, I mean the syllabus in the sense they have actually deleted your heat capacities. All those things are deleted. I'm just letting you know that these are all other things. Okay, for a polyatomic gas, right? It is going to be, I think, 7/2 RT. Okay, CV value. I'm talking only about the CV values, not the CP values. Okay, but let me check these two and let you know after the break what exactly are the values. Don't worry about it. But this is correct. Okay, for a monatomic gas, it is going to be 3/2 R into T. Okay, right. So this again is coming from the contribution of the translatory motion, rotational motion, and the vibrational motion. Okay, so translatory motion will have some contributions, rotational motion will have some contribution, vibrational motion will have some contributions, and accordingly you'll be able to calculate the overall CP values. Okay, right. So these and all are the things you have to understand about your heat capacities, how they related to atomicities, how they related to the amount of motion, and how it's related to your heat conductivities. All those things you have to understand. That's it. Very, very simple. Okay, right. Moving on, people. Moving on. So now we are going to see your zeroth law of thermodynamics. Okay, and this law is also called as common sense law. Right? So means what? Means if you have a little common sense, right? Obviously, you'll be able to understand this law. You don't need to know science for you to understand this law. Okay, right, people. And you will be able to see that whatever be the laws of thermodynamics you will study, zeroth law, first law, second law, third law, there are 4 laws, 0, 1, 2, 3. Okay, now all these laws are actually, observations made from the universe. Okay, they just observe that something is happening, and based on that, they will be able to give a law. Okay, right. So people, before we move on to the zeroth law of thermodynamics, let us understand certain concepts. Okay, right. So I have 2 bodies, right? Now this is a hotter body, right? This is a colder body. Okay, now I'm keeping them in contact, right? I'm keeping them in contact, right? So we know that the heat is going to flow from the hotter body to the colder body. Is it not? The heat is going to flow from the hotter body to colder body. Now the question is, until what time or until what period this heat flow will happen? Is it going to happen continuously throughout infinite amount of time? Obviously not, isn't it? There is going to be a time period where there is no heat flow, right? So this is where the temperature comes into the picture, right? So if at all I say that this is temperature T1 and this is temperature T2, obviously T1 is greater than T2 because it's a hotter body, right? So you understand that the heat flow will happen. The heat flow will happen until both the balls or both the bodies are going to attain some common temperature, right? Some common temperature, until some common temperature is reached, right? Both of them, say 25 degrees Celsius, 25 degrees Celsius. Okay, I'm going to reach till this time the heat will flow. The moment you reach both 25 degrees Celsius, there is no heat flow. The heat flow will not be there. Okay, so at this particular point, when 2 bodies are there and there is no heat flow between them, these kind of situations are what are called as thermal equilibrium. Okay, what is thermal equilibrium? When I say 2 bodies are in thermal equilibrium, then there is no heat flow. There is no net heat flow between the bodies. Okay, or in other words, I can also tell that they have same temperature. Right, 2 bodies are there, different higher temperature, lesser temperature. Now I keep them in contact, so the higher temperature will reduce, lower temperature will rise, and they'll eventually be at a common point. And at that time, we say that there is no heat flow, and at that time we'll tell that these 2 bodies are in thermal equilibrium with each other. These are very, very simple things. Okay, right. So zeroth law of thermodynamics is talking about the thermal equilibrium. Okay, now it's very simple to understand, people, right? We have 3 bodies, A, B, and C. Okay, and it's very, if they say that if A and B are in equilibrium separately, right, and if C and B, A and B, right, if C and B are in equilibrium, right, then it is very much understood that A and C are also going to be in thermal equilibrium with each other. Because if there is no heat flow between this and this, if there is no heat flow between this and this, obviously there is no heat flow between this and this also. That is very much understood, right? That is why we call this as common sense law. Okay, this is all about particles being in thermal equilibrium. If 2 bodies contain separately in thermal equilibrium and that body with another body in thermal equilibrium, obviously the first one and the third one, it is understood that that is also going to be in thermal equilibrium. Okay, right. So that is about your zeroth law of thermodynamics. Okay, fine. Now next thing, or what I want to introduce to you is the concept of something called as internal energy. Right, internal energy of a system. Okay, right. So what do you mean by internal energy, right, people? So this internal energy, nothing internal energy, we have some internal energy even if you don't eat, right? Even if we eat, we'll have some energy. If we don't eat, we'll not have energy, something like that. So our body has some internal energy with us. We have our own energy. Every atom molecule will have its own energy. Okay, so that energy is what we're trying to speak about here, right? So internal energy is nothing but the sum of potential energies plus the kinetic energy, sum of all the potential energies and kinetic energy which can be possessed by a body, right? And not coming from external factors. By itself it is going to have, right, sum of all the potential and kinetic energies you are going to have, right? That particular total sum is what is called as your internal energy. Okay, it is denoted by the letter U, or sometimes it is used as E, right? So in your textbook, they will use U, right? So we'll also use U. Okay, we'll also use U, but I will prefer using E. Okay, fine, we'll see what am I going to use depending on my mood. Okay, so internal energy is nothing but the sum of all the potential energies and kinetic energies produced by the molecule. So I can write it like this: internal energy U is equal to potential energies, total potential energy, sigma potential energy, plus kinetic energy due to translatory motion, kinetic energy due to vibrational motion, plus kinetic energy due to rotational motion. And you have to do this for all the molecules, right? Not for one molecule. Say for all I have 100 molecules, all the 100 molecules, individual translation, vibration, rotation, potential energy, everything has to be calculated, right? And that whole sum is what is called as an internal energy, U or E, we call it. Okay, right? And this absolute internal energy, that is your sum of all these values, absolute U, cannot be calculated, cannot be found out, right? Why? Because we understand we have billions and millions of molecules. First, you have to understand that molecule is undergoing translation, rotation, or vibration. You have to calculate its kinetic energy and then sum it up. Huge process in reality, which is never ever possible. Okay, which is never ever possible, right? So what we can calculate or what we can find out is actually the change in internal energy, del U or del E, that is change in internal energy, right? That can be calculated. Okay, that can be calculated. All right. Okay. Now, what are the ways by which you will be able to change the internal energy? Okay, we'll not be able to say, okay, this is the initial energy, this is the final energy. No, but we can tell that, okay, it has increased by this much, it has decreased by this much. That will be able to tell. That is what I'm trying to say. Absolute internal energy cannot be measured or cannot be found or cannot be calculated. But the change in internal energy, yes, it can be calculated or it can be found out. Okay,
Sir,
now yeah, go on.
Sir, could you tell me why absolute U cannot be?
Yeah, it's very much understood. Say, assume that I have some 1 lakh molecules. Okay, some zeros. Okay, for the individual molecules, each and every molecule I have to calculate potential energy. And if at all, they first have to understand whether they're going to undergo translation motion, rotational motion, or vibrational motion, or all three are there, or only two are there. And first I have to find that out, and I have to find the kinetic energy associated with the translation motion, vibrational motion, rotational motion. This is for one molecule, and I have to do this for 1,000 or 100 and lakhs and billions of molecules, right? So they are very microscopic, first of all, right? Finding them out at what position they are in and what kind of motion they are undergoing, impossible in reality, right? So that is why we say that absolute internal energy cannot be found out. Yes, understood?
Okay, sir, got it.
Right? Good. So all that we can find is delta U or delta E, right? So the next question comes to our mind is, how and all we'll be able to increase or decrease the internal energy? What can cause change, right? What can cause change in internal energy, right? There are two possibilities. One, if you give some heat to the system, or if the system loses heat, or if you give some heat to the system, that is one possibility. Obviously, what will happen? The heat will be absorbed and the kinetic energy values will change. The molecules will move faster, faster vibration, faster rotation, faster translation motion, right? So one possibility is that by giving some heat or by removing some heat to the system, right? That is one possibility. Second possibility is by doing some work, that is W, right? Either the system is doing work or you are doing work on the system, right? I can write system working, or work is done on the system, not one, on the system. Either way, we'll speak more in detail about this. What do you mean by work is done by the system, work is done on the system? We'll try to understand later. But for now, what you have to understand is, either if I supply heat or I remove heat from the system, the internal energy will change. Or if the system does some work, or when we do some work on the system, again you will see that the kinetic, internal energy will change. Two possibilities. Okay, right. So now people, right? Now what I'm going to do is we have three things of us: delta E, Q, and W we have. Okay, now we understand that all these three are going to be interconnected, right? The change in internal energy, the amount of heat, and the work done, right, are actually going to be interconnected. Right, now we understood how delta E is individually connected with Q, how delta E is individually connected with work, but how is it these two are related? That is very much understood. Right, now it's like this. Say for example, right, I have a system, I have a piston like this, I have a gas. Okay, now this is at some equilibrium, this is the piston is not moving. Okay, now what I'm doing is I am heating this. Right, I'm heating this. So what will happen? They will go hit the piston. So can I say the piston is going to move up? Now it would have gone up like this by heating. Right. So obviously, what you understand, the gas molecules here are actually doing some work. How are they doing some work? They are pushing the piston up. Right. So by supplying some heat, right, by supplying some heat, you are actually able to make the gas molecules work. Right, the same exact thing happens only in your power plants or in your vehicles for that matter. How is happening? If there is petrol, right, the petrol is getting burnt. Right, the petrol is getting burnt, lot of heat energy is produced. Okay, and that heat energy is used for moving the vehicle, right, kinetic energy. Right, so either way you can understand that Q, that is amount of heat, and the work done can be related also. They can also be related. And obviously in this process you're supplying heat, the work is changing, definitely the internal energy will also increase or decrease, doesn't matter whether it's increasing or decreasing, we'll understand later, but you will see that the internal energy will change in this process. Okay, so that is why we say this delta E, Q, and W are interrelated. Okay, right, so how are they interrelated exactly is what is given by your first law of thermodynamics. Right, now first law of thermodynamics, if you look at the statement, it is nothing but the law of conservation of energy. Law of conservation of energy. That is nothing. Energy can neither be created nor be destroyed, but can be transformed from one form to another form. That is the statement. It's very simple. Law of conservation of energy is the statement of first law of thermodynamics. But if I look into the mathematics of the first law, right, this is how you'll be able to write. Okay, now what we said that the internal energy can be changed by giving some heat or by doing some work. Right, so we can understand that the delta E can appear because of change in heat or by changing the amount of work done. That's it. This is your mathematical equation for the first law of thermodynamics. Okay, delta E is equal to Q plus W. Right, now there are various ways of writing this equation. We can also write it like this. Right, Q is equal to delta E plus W. Right, you can ask, sir, what is happening? The signs are not changing. If Q is going here, this is coming here, there I should have a negative sign coming, anything is coming. It is all about how you perceive it. Okay, so this statement, what we can understand is the delta E can be changed either by changing the amount of heat or by doing some work. That is what I understand. Now this, what we understand from this, the amount of heat given to a system, right? I give some amount of heat to the system. That heat can be either used for increasing the internal energy or for making the system do some work. Okay, I hope you understand this particular statement. This particular mathematical equation says that if I give some amount of heat to the system, right, that can be used to change the internal energy or that can be used by system to do some work. Very simple. Both these are absolutely right. Okay, both these are absolutely right. Now, why is there not the signs are not changing even though we are actually moving the terms in the equation? You see that the signs are not changing because there are some sign conventions we will follow. Okay, we will follow. So both these things are correct, but don't use this equation. Go for only this equation. Okay, delta E is equal to Q plus W is what we are going to follow throughout the chapter. Throughout the chapter, same equation will follow. Delta E is equal to Q plus W. Okay, this is your mathematical equation of the first law of thermodynamics. All right. Okay, fine. Now, people, let us talk about W for a while. right? We understood what is internal energy. We have spoken so much about the Q, and let us talk about W also. What do you mean by work done? What kind of work are we going to consider here? All these things we'll try to understand. Okay, just give me one moment. I'll be back in 10 seconds. Just give me, I'll be back. Okay. Right. So as I told, we spoke so much about delta E, we spoke about Q. Let us talk about W. Okay. What do you mean by this work done? So people, in this part of the chapter thermodynamics, right, we'll be speaking only about the PV work, right? That is pressure volume work is the only type of work we'll be seeing, right? So we'll be only seeing this piston kind of arrangement, okay? And that is moving up or moving down, compressing, expanding, expansion. So those kind of work only we'll be seeing. Okay, right? There are other types of work, but we are not going to deal with them for now. Not for now, not in this chapter. Okay, right. So people, this work, this PV work, right? We know in general work done, W, I know from your physics that it is equal to minus F dot S, right? There is an, again, don't worry about the negative sign for now. Don't worry about it. Right? This is nothing but force into displacement, right? Force into displacement is the formula for your work done, isn't it? Right? So what we'll do is we will convert this equation a little bit, right? So what we'll do is F, now I know P is equal to F by A, that is pressure is equal to force by area, isn't it? So can I write F is equal to pressure into area? Right, so I can do that because we're talking only in terms of pressure and volume. That's why I'm actually changing this equation like this. Okay, so I can write what is that? Force as pressure into area, right? And what we have is some distance, right? Now we understand, people, this, right? This area into some other length is actually going to give us volume, is it not? That is actually going to give us some volume. So the final equation for work done, right? I told you there was a negative sign also. We have to put a negative sign also. So that is going to become minus P external into delta V. This is the equation which you have to remember. Okay, right? Work done is equal to minus P external pressure, not the pressure of the gas. That means there are two pressures here. Look at this. Okay. So there is some gas inside. Okay, this is the pressure of the gas, but if I exert some pressure here, that compresses. So in this case, we have to consider the external pressure only in the equation. Please understand, we are not taking the pressure of the gas. Okay, right? Sometimes the external pressure and the pressure of the gas can become equal. Okay, for example, look into this, right? Say I have a system like this. Okay, and I have this thing, right? Say the pressure of the gas is P1. Okay, and basically you see that the piston is not moving at all because the external pressure is equal to the pressure of the gas, right? Only then the pressure piston will not move at all. It will stay in the same position like this, right? Now what I do is, now I'm heating it. Now what will happen? The piston will move up. The piston will move up like this, right? Now obviously the pressure will change to P2. Right? So again, in this case, the final pressure, the external pressure now again is going to become equal when I stop heating, right? Or when I continuously heating, but constant supply of heat I have, constant supply of heat. right? At that time, again, you will see that the external pressure will be equal to the the pressure of the gas, final pressure. Okay, so sometimes it might be equal, sometimes it might not be equal, but we always take what? We always take to be safe, we always take only external pressure. Okay, we always take only external pressure in the equation for work done. So again, I write the equation for you. W is equal to minus P external into change in volume. That's it. Okay, now people, one very important point. Now, W will be generally in terms of joules, right? W will be generally in terms of joules, right? Now we write pressure in terms of ATM most of the time and volume in terms of liters, isn't it? So how is it that you multiply ATM into liters and you're getting joules? No, that is not possible. Okay, so what you have to do is, people, ATM into liters, you have to multiply this value by 101.3, so this entire thing can be changed into joules, right? This entire thing can be changed into joules. Okay, so you will use external pressure in terms of ATM, change in volume in terms of liters, that is not equal to joules. The multiplication is not equal to joules, right? So we have to convert it to joules. So for that, we'll multiply this value, entire value, whatever we get, into 101.3. Then only you will be able to get the value in terms of joules. Okay, right? Fine. So that being said, I think we can, okay, one more thing also, I think, right? So that is about the work done. Very simple. When the expansion or the compression happens, there will be some work done. Okay, and we have to understand that that is the formula, that Px minus P external del V is what we have. Okay, now one last thing, or actually last two things I'll tell you. There is something called as sign conventions. We have to follow certain conventions of signs. Positive sign, negative sign, when will you give? All these things you have to understand. Okay, so sign convention is for two things. One is Q, another one is W. Okay, right. So now Q, when Q is added to the system, that is heat added to the system, right? Now that should be positive value. Okay, when I say system gains 10 joules of heat, then I will tell that the Q value is plus 10 joules. The system gains 10 joules of heat means the Q value is plus 10 joules. All right. Okay. Another way is that the system is heat is lost. When heat is lost by the system, right? Now, whatever be the amount of heat lost, that value should be negative value. So if I say 10 joules of heat is lost by a system, right? Then I will tell that the Q value is minus 10 joules. Okay. Heat gained is positive. Heat lost is negative. Okay. This convention we will follow. So you have to read the questions very carefully. Then only you will be able to assign the signs. Okay. Next. W, coming to W, right? So we have work done by the system. We have work done by the system. If system does work, right, that is going to be a negative value. Okay, when system does work, it is going to be a negative value. And if work is done on the system, right, when we are doing work on the system, and the surrounding is doing work on the system, right, that is going to be positive value. Okay, when system does work, it is negative. When the surrounding does work, it is positive. It is positive, right? System doing work, negative. Surrounding doing work on what? On the system is going to be positive. Okay, now how are we going to understand this? Is very simple, people, right? See, one situation is like this, right? So we have a piston like this, and say I have a 1 kg box on top of this. Okay, and it is in equilibrium. The piston is not moving. The pressure of the gas, right, and the pressure exerted is same. That's why the piston is not moving. Now what I do is I am heating it. Okay, now what will happen? I know that the individual gas molecules will go hit the container with now greater force, so the piston will move up, right? So who is doing work? The system, that is the gas molecules in the system are doing work. So in this case, the work is negative, right? Now another case, like look at this. I have a 1 kg box like this on top of this, and this is an equilibrium. Now what I do is I add one more 1 kg box. Now what will happen? The piston will move down, right? Now who is doing work? this extra 1 kg which you are adding, that is the one which is doing work. That is pushing the piston down, right? So in this case, the work will be positive because the work is done by the surroundings on the system. That compresses the gas by adding this 1 kg. In this case, who is doing work? The system is doing work, right? Okay, so that is all you have to understand. Whenever system does work, it is negative. Whenever the surrounding does work on the system, that is going to be positive. Okay, and in physics, okay, in physics, you will exactly do the ulta, right? They will tell work done by system is positive and work done on the system is negative. Okay, they will exactly tell the opposite of what we saw now. But in chemistry, this is what we follow. Okay, why is it like this? If you ask me, because physicists are actually, interested in the work output. I do something and I'll be able to get the work done by system. That is there. That is what they want. So they give it a positive value. We are not interested in that. We are actually interested in how the dynamics is changing, right? We are interested in the chemistry part of it, not the work done, right? That is why we have this kind of stuff. But both are correct. There is only convention, right? It's all about how people have been following, and we are following that. That is what is convention, tradition. Right? So we always take work done by the system is negative, work done on the system by the surrounding is positive. This is what we always take. Okay, and regarding your Q, we say that heat added to system is positive, heat lost by system is negative. Okay, so these two sign conventions we have to very strictly follow. And most important point is, without the formula W is equal to minus P external del V, you will always get the value in terms of pressure and volume, that is atm in liters. If you want to convert it into joules, you have to multiply it by 101.3. Okay, you have to multiply it by 101.3 to get the answer in terms of joules. Okay, and one last point, and then we can go for solving some questions. Right, so the delta E which you're talking about, that is the change in internal energy, delta E or delta U, however you call it. Okay, now this is directly proportional to change in temperature. Okay, more and more the change in temperature, more and more will be this thing. This is nothing but a form of heat energy only. Okay, so I can directly give you one equation. Delta E is equal to number of moles into CV of the gas into del T. NCV del T is the formula which we have to remember for delta E, right? Delta E is equal to N, number of moles, right? CV, molar heat capacity at constant volume, right? And delta T is the change in temperature in Kelvin. Okay, so this formula again you have to remember. Delta E is equal to NCV del T. So if at all you know the change in temperature, you actually know what is the delta E value, because this value is known. CV for all the gases are known, right? A number of moles obviously you need to know, right? Number of moles and the change in temperature, you know, you will be able to easily calculate what is your delta E. Delta E is equal to NCV del T. Okay, now one more thing also I can tell. This delta E, okay, among this Q, W and delta E is a state function, right? Because we understand, right? It is going to depend only on the change in temperature, nothing else, right? But this Q and W are going to be path functions, right? Delta E is state function, Q and W are going to be path functions. So if I ask you, I have a PV curve, right? I am moving from state 1 to state 2. This is point A to point B. Okay. And I'm coming back. The arrow marks goes like this. Okay. And I'm coming back to point A again. Okay. Can you tell me what will be the change in delta E? What will be the change? What is it? I did not hear what you said. Yeah, 0. Exactly, because the initial state and the final state are same. So for example, you understand that here the pressure was P1, volume was V1, temperature was T1. Here the pressure is P2, V2 and T2. Okay, right. So now finally what is happening here? T1 is the initial temperature. T1 is the final temperature also. So if you put it in the equation, T1 minus T1 means what? 0. So delta E for a cyclic process, right? Delta E always, delta E for a cyclic process should always be equal to 0. but work done on W will not be, work done on Q will not be 0 for a cyclic process. Okay, delta E for a cyclic process is always going to be 0 because it's a state function. Initial and final states are same, so we understand that it is going to be 0. But in the case of what is the Q and W, no, you are not going to have 0. You will have some finite value to be present. Okay, right? What is the time? Okay, guys, we'll take a break. Okay, after the break, we'll do some problems on all of these. Okay, the first law of thermodynamics, work done, and your delta E, all these things, we'll do some problems. Okay, you can take the break. So time is almost 12:26. We'll meet by 12:36. Right, on 12:27 it is. So we'll meet by 12:37. Okay, 10 minutes of break. Okay, I hope you guys are back. Shall we start, people?
Sir,
Yes, sir.
Yeah, tell me.
sir, could you show that formula once?
Yeah,
Just
the
could you just scroll?
work
No,
done
sir.
formula.
Up. Yes, sir.
Yeah,
Delta E. This only.
okay.
Thank you, sir.
Yeah. Okay, people, write in the question. Yeah, you have to boil it. No. At last, I can add honey. Okay, people. So the question was like this: 8 grams of O2 gas, 8 grams of O2 gas at STP, 8 grams of O2 gas at STP is expanded so that the volume is doubled. Okay, find the work done. Right, so I'll repeat the question. 8 grams of O2 gas at STP is expanded so that the volume is doubled. Find the work done. So you can tell me the answer in liter atmosphere only. Okay, find the work in terms of liter atmosphere. That's the unit. Okay.
Five 5.6.
5.6 of minus plus anything.
Plus.
Okay, we'll check. Right. So we have W is equal to minus P external into del V. Right. Okay. Fine. Right. So what is the external pressure here, people? What is the external pressure here?
1 atm.
1 atm. We have given that at STP. Right. At STP, I know standard pressure is 1 atm. And the standard temperature is 0 degrees Celsius. That is not going to be of any criteria here. Don't worry about it, right? So we have P external del V. So the external pressure is 1 atm into change in volume. Now we understand that the volume is getting doubled, right? So it is basically going to be V2 minus V1, right? Minus
Sir?
of, yeah, tell me.
Sir, I guess it's negative, sir. Negative 5.6.
It will be negative only. Please understand, people, whenever expansion happens, right, the work done will be negative, right? And whenever compression happens, right, the work done will be positive. Remember this. It is going to come from the formula eventually. If you calculate it properly, eventually you'll get that answer only. Okay, right. So we have minus 1 into V2 minus V1, and we understand that V2 is twice the volume of V1. Right, initial whatever was the volume, the final volume is doubled than the initial volume, right? So I can write this as W is equal to minus 1 into V2 minus V1. V2 minus V1 will become that is 2V1 minus V1, right? 2V1 minus V1. So W is equal to minus of 2 into V1. We don't know what is the initial volume, people. We really don't know. Okay. So this is where we have to use the ideal gas equation, right? We don't know the final volume or the initial volume, nothing we know, right? So we can calculate that with the help of ideal gas equation. We have PV is equal to nRT, right? Okay, now I know what is the pressure, I know what is the number of moles, I know what is the temperature, everything we know. right? So all that we need is only V1. Okay, so P1, V1, T is constant. Let us keep T constant. Okay, right. So the initial pressure of the gas is 1 atm. Volume I don't know. Number of moles I can calculate. Number of moles of O2 is given mass 8 grams divided by molecular mass of O2 is 32 grams. Right? That is 1/4. Okay, into R value using liter atmosphere and atm. That is going to be 0.0821 into temperature is now 0 degrees Celsius. That is going to be 273 Kelvin. Okay, 273 Kelvin. Or is there any other better way? Is there any better
Yes,
any
sir.
other better way? Huh?
Sir,
Yeah, tell me.
sir, at STP will be 22.4 liters, right?
Exactly. So people at STP, I know 1 mole of any gas will have a volume of 22.4 liters. But how many moles I have? I have only 1/4 moles. Right? So can I tell this will be 1/4 of this? That is going to be basically 5.6 liters. That would have been the volume, right? If at all you calculate this, you'll get the exact volume like that only. You will exactly get the volume as 5.6 liters approximately. That's what you'll get. Okay. Or if at all some other pressure and some other temperature is given, definitely you would have gone for this equation. PV is equal to nRT to find the VV1 because you know all the other things, right? But in this case, since STP is given, we can tell that 1 mole of any gas will occupy a volume of 22.4 liters. Now I have only 1/4 moles. We calculate 1/4 moles. So it is going to be 5.6 liters, right? So done. That's the answer to this question. So 2 into V1 is, this is what is your V1 initially, right? So 2 V1 is what is the work done. So minus 2 into 5.6. So you must be getting the answer as minus 11.2 liter atmosphere. This is the final answer. Minus 11.2 liter atmosphere is what is going to be the final answer. Okay. I hope everybody is following, right? Okay, people, next question. Right?
Sir,
Tell me.
sir, how is it 11.2?
Okay, so we have to calculate V1, right? So V1 is basically, if I have 1/4 moles of this, initial volume would have been 5.6 liters. Okay, now we calculate W to be minus 2 into V1. What is V1? 5.6. So 2 into 5.6 will become 11.2. That's it. Yes.
Understood, sir.
Right, done. Very, very simple. Right. Okay, next question, people. A sample of an ideal gas. Second question I'm telling. Right. A sample of an ideal gas underwent an expansion. A sample of an ideal gas underwent an expansion against a constant external pressure. Against a constant external pressure of 1 bar from 1 meter cube, 10 bar and 273 Kelvin, to 10 meter cube, 1 bar and 273 Kelvin. Okay, to 10 meter cube, 1 bar and 273 Kelvin. Okay, and the question is calculate the work done. Calculate the work done. Right? So people, again, I repeat the entire question. A sample of an ideal gas underwent an expansion against a constant external pressure of 1 bar from 1 meter cube, 10 bar and 273 Kelvin. This is the initial conditions of the gas, initial state, pressure, volume, temperature of the gas, right? To 10 meter cube, 1 bar and 273 Kelvin. That is your final state, right? They're asking you what is the work done by the system. Calculate the work done. So get the work in terms of meter cube and
Sir,
Pascal.
bar and ATM is the same.
That's what you get. You keep the units as such. Okay, meter cube Pascal. That's the unit I need for work done.
Sir, is it 9 into 10 power 5?
Okay, we'll check. So W direct formula minus P external into del V. Okay, so external pressure is 1 bar, people. They have taken constant external pressure. They have mentioned that pressure only you should use, not 10, not 1 bar. I mean, 1 bar is here, but you should not be using this one, 10 bar. No, we have to use the external pressure into the total volume in final change in volume, right? So this is 1 bar into the change in volume. So it is basically going to be V2 minus V1, right? Minus of 1 bar into V2 minus V1. So it is going to be 1 into final volume is 10 meter cube, right? Minus initial volume was 1 meter cube, right? That's it. So what is the answer now? That is going to be 9 meter cube Pascal. That's it. Or Pascal meter cube. That is minus is what is going to be the answer to this question. W.
Sir,
Tell me.
sir, but we also have to mention the units of work done, right? Like in joules or.
Yeah, exactly. The unit I want is only in terms of meter cube Pascal. That's it. That's the unit. Are you able to
Okay, sir.
understand? Right? So if I asked
Yes,
you,
sir.
would have converted into joules, please understand pressure into volume. If I do in SI units, that is, if I do it in terms of Pascal is the SI unit, right? Okay, so Pascal is the SI unit and volume SI unit is meter cube. Then you will multiply that, you get the answer in joules of joules. Okay, directly this answer is minus 9 joules. Directly you can tell. Oh, this is not Pascal, no, this is bar. Okay, I'm so sorry.
Yes.
Yes, sir.
Sir.
That's what.
Right, that's the bar. So if you have Pascal and meter cube, if you multiply directly, you're going to get joules. Okay, right? But if you have any other unit, you will not be able to tell as joules. You just have to keep the unit as such. Right? And don't worry much about the conversions, right? I told you one conversion, ATM liters into 101.3. Into 101.3, you are going to get the answer in terms of joules, right? If at all you have anything like this, right? All you can do is meter cube is already there. Okay, you just have to convert bar to Pascal. I know what is the conversion, right? I know 1 bar is 10 to the power 5 Pascals. Is it like this?
Yes, sir. Yes, sir.
Right, that's it. So now you can just convert that and you can put this here, right? And maybe if you just multiply this by 10 to the power 5, you're going to get the answer in terms of joules. Okay, that also you can do.
Sir,
Right?
but then
On,
we'll have to convert the meter cube to liters, right?
no, not required. What do we need in terms of SI unit? SI unit is Pascal and meter cube. Then if you multiply, you're going to get joules. Already meter cube is there. Right? So you have to convert only the bar to Pascal, then you will get the answer directly in terms of joules. In this case, it is not joules, it is minus 9 into minus 9 bar meter cube. That's a unit here. Okay, or I can also write this as minus 9 into 10 to the power 5 joules, or minus, or I can even write it as minus 9 into 10 to the power 5 what is it, meter cube Pascal. Meter cube Pascal is nothing but joules. Yes, understood.
Yes, sir. Understood, sir.
Okay, fine. Good, good. Okay. Next question. Okay, next question. 5 moles of an ideal gas. 5 moles of an ideal gas at 27 degrees Celsius. At 27 degrees Celsius is allowed to expand. Isothermally. Okay, this is a new word. I'll tell you what is this. Don't worry. For in this question doesn't matter much. Right? 5 moles of an ideal gas at 27 degrees Celsius is allowed to expand isothermally, means at constant temperature. When I say isothermal, means constant temperature. Right? So 25 to 27 degrees Celsius is maintained even throughout the expansion. Okay, right. So 5 moles of an ideal gas at 27 degrees Celsius are allowed to expand isothermally from an initial pressure of 10 atm to a final pressure of 4 atm against a constant external pressure of 1 atm. Against a constant external pressure of 1 atm. Find the work done. Find the work done. I will repeat the question, people. 5 moles of an ideal gas at 27 degrees Celsius are allowed to expand isothermally from an initial pressure of 10 atm to a final pressure of 4 atm against a constant external pressure of 1 atm. Find the work done. That's the question. Now, in this case, the volume is not given, but the pressure is given. So you know what to do. Right? Think about it. And I want the answer in terms of joules. Okay. See, I'll just give you one thing, right? So remember that R value is what is the thing? R value, if you use it as 8.314, that will directly give you the answer in terms of joules. That is all that you have to understand. Okay. Don't worry about the other units, right? If you use the R value as 8.314, directly you will get the whatever the value you're getting in terms of joules. Okay, right.
Sir, then pressure also we don't need to convert into Pascal.
Nothing, no conversion, nothing required.
Okay, sir.
Sir, is it minus 1870?
Minus 1870. Okay, options are there, might be correct. Yeah, minus is okay because it is expansion. Should be correct, I guess. Okay, so we have W is equal to minus P external into del V. Okay, so external pressure is given as 1 atm. Okay, minus 1 atm into V2 minus V1. That's all we need. Okay, right. So they have not given us volume 2 and volume 1. That is the final volume, initial volume is not given, but the initial and final pressures are given. Right. So now we definitely have to go for ideal gas equation. There's no other go. Right. So we have W is equal to minus 1 atm into V. How can I write? nRT. Now T is constant, so we can use T common, right? So nRT divided by P2 minus nRT divided by T1. That's it. I know number of moles, I know R, I know T. Right? The T is constant. It's an isothermal process, so temperature is constant throughout the process. Okay, right. So we can take actually nRT outside, right? We can actually take nRT outside because all these are constant term. So it should be minus 1 into N. They have given number of moles to be how much? 5 moles of a gas. R value I said that I should use as 8.314, and temperature is 27 degrees Celsius and 300 Kelvin. Right? You should not put a Celsius degrees, people. Okay, into 1 by P2. P2 is how much? Final pressure is 4 from the initial pressure of 10. Right? So you will be getting what will be the answer? I think say it is minus of 5 into 300 is 1500. 1500 into 8. So will be 12,000 approximately. Right? Approximately it is 12,000 people. Okay, approximately 12,000 by this thing is 0.25. 1 by 4 is minus 0.25. 1 by 10 is 0.1. Right? So you should be getting it as minus 12,000 into 0.15. Right? So yeah, you should be getting the answer as minus 1870.6 joules exactly. Right? These are some approximations here. Right? But if you do the calculations perfectly, you should be getting the value as minus 1870.6. Okay. Right. Fine. Similar questions. Yeah, this question you can take. Right. The question goes like this, people. Take down. Okay. Temperature of 1 mole of helium gas. Temperature of 1 mole of helium gas is increased by 2 degrees Celsius. Temperature of 1 mole of helium gas is increased by 2 degrees Celsius. Find the change in internal energy. Find the change in internal energy. Okay, that's the question. And I want the answer in terms of calories. So what should be the R value you should use, people? If I want the answer in terms of calories, yeah, 2. Remember that the R value should be 2 if I want the answer in terms of calories. If at all I want the answer in terms of joules, then you would have used 8.314. It's going to get switched off. There is no charging. Yes, this much time it takes. What is the formula? Delta E. We're
1
talking
minute.
about the change. Okay.
Sir, is it 5?
5 calories. No. Very simple formula, people. Yeah, tell me.
Sir, no, sir. I didn't get the answer. How to calculate the specific heat capacity at
I
constant
told
volume?
you for a monoatomic gas,
Sir,
the
how is
CV value
helium
is
gas
one.
monatomic?
Obviously, helium is monatomic. Helium, it will
Sir,
be like this,
then-
it will be like this, like C2. No, right?
Sir, then
Monatomic
3,
only.
sir.
3. Okay, we'll check. Right. So we have delta E is equal to NCV del T. That's the formula. Okay. Now, a number of moles is given as 1. Now, I know helium is a monoatomic gas. The moment you see a monoatomic gas, I know the R value is 3 by 2 R. I'm sorry, it's not 3 by 2 R, not T, 3 by 2 into R. Right. That's the, what is that? Heat capacity value. Okay. So I know this thing is 3 by 2 into R value. I said that I want the answer in terms of calories. So you'll use 2, right? Into change in temperature. Change in temperature is 2 degrees Celsius or 2 Kelvin, doesn't matter. It's 2. That's it. Okay. Right. So that's all we have. So 2 gets cancelled. So we have 3 into 2 is 6 calories. That's the answer to this question. Okay. Right.
Sir,
So
you told for diatomic gas, you will give the formula, sir.
for diatomic gas,
No, sir. For monoatomic gas, it's 3 by 2 into RT.
R.
Similarly,
No,
for
3 by 2 into
diatomic
R.
and
That's it.
I'm sorry,
The-
R, sir. So for the diatomic and polyatomic gas, you told you would give after the break.
Yeah. So for diatomic gas, it is 5 by 2 R. Okay, for diatomic gas, it is diatomic or polyatomic for that matter. Okay, they will not have much changes, right? For diatomic gas and polyatomic gas, you use 5 by 2 into R, CV value. Okay, that's the value you should use, go for. Right, diatomic or polyatomic, we'll go for 5 by 2 into R. Okay, that's the value you use. Okay, so the answer to this question will be 6 calories. Very simple. Okay, right? So these are all the questions I wanted to do. Okay, now let us move on to the first law and we'll see how or not we can manipulate it. Okay, right, people. So we know what is first law of thermodynamics, the mathematical equation of first law of thermodynamics. We already know delta E is equal to Q plus W. All right. Okay. Now, before we move on to this, right? Actually, let us. There is a formula for W. One more direct formula for W we have. Okay, that also I'll let you know. So W can also be written as delta NGRT. Okay. Now this is another equation you can remember. Delta NGRT. What do you mean by delta NG? It is very simple. The delta NG is, or let us take some example. Then will make more sense. Right. See, look at this. We write W as P external minus P external into del V. Correct? Okay. Right. So now minus P external del V, this is like PV, right? This is like P into V, right? So we can also write this as nRT directly. Okay. But now we have, what you have to understand is we have to include only gaseous molecules. You have to include only gaseous molecules because gases only will undergo expansion, gases only will undergo compression. Solids and liquids, ideally speaking, they should not be undergoing compression or expansions. Okay, right. So this P into del V, I will be able to write as delta NG into RT. Now, what is this delta NG? Let me tell you. Right. So delta NG is equal to total stoichiometric coefficient of gaseous products minus total stoichiometric coefficients of gaseous reactants. Okay, right. So what am I trying to say is, look at this, right? So like for example, let me tell, like for example, say let us take what we can take. Okay, say let me take Fe in the presence of HCl. Okay, Fe plus HCl reaction I'm taking. Okay, now I know what I'm going to form. FeCl2 plus H2 gas is going to get evolved. Right, this is aqueous solution. Okay, this is solid. Okay, this is also aqueous solution. I know this is gas. This one we know already. Right. So if I have to, now if I ask you, what is the work done? What is the work done at 27 degrees Celsius? If I ask you for this polar reaction, right? In this polar reaction, I'm asking you, what is the work done at 27 degrees Celsius? Right now, all that I have to use is this formula. W is equal to delta NG/RT. Okay, right? How do we use this? It's very simple. How first to calculate delta NG. Now, delta NG I told you as total stoichiometric coefficient of only the gaseous products, right? Gaseous product I have only one, H2, right? So the stoichiometric coefficient is one. It is one, right? Okay, you have to balance the equation. Don't worry about it. Okay, this is balanced now. Okay, so the gaseous reactant stoichiometric, gaseous product stoichiometric coefficient is 1. Okay, and in the reactant, you understand there is no gas at all, so this should be minus. Okay, so the delta Ng value is 1, right? So how will you calculate W? W equal to delta Ng, that is 1. R value, depending on the unit what we want, depending on whether it's going to be calories or this thing. Temperature is 27 degrees Celsius, so it is 300 Kelvin. So it should going to be 300 R. This is the value. This is the work done in this particular reaction. Right now, if I ask you another case, say I have N2 plus 3H2 giving 2 ammonia. Okay, and I'm asking you, what is the work done at 27 degrees Celsius? Right, what is the work done at 27 degrees Celsius? What will be your answer? Quickly calculate, people, for this reaction. Right, I'm asking you, what is the work done in doing the reaction? Yeah.
Sorry.
Tell me.
1 second, sir.
At 27 degrees Celsius.
Sir, 200 R. No, sir.
Are you getting negative signs?
1 second, 1 second. Oh, sir, 600 R.
Negative sign, positive sign, anything is there? Okay, fine. W is equal to delta Ng into R into T. So delta Ng, let us calculate. All these are gases here. Right? So in the product side, the stoichiometric coefficient is 2. Okay, minus. In the reactant side, we have 3 for H2 and 1 for N2. So totally 4. So you'll be getting the delta Ng value as minus 2, not plus 2. You have to be very careful in this. Okay, W is, delta Ng is minus 2. Okay, now go for the formula. W is equal to minus 2 into R into 300. So you should be getting the answer as minus 600 R, not plus 600. Okay, right? Total stoichiometric coefficient of gaseous products minus total stoichiometric coefficient of gaseous reactants is what you have to take. So if at all you get a negative sign, you have to include the negative sign. Very, very, very important. Okay, very simple questions. Okay, people. Now moving on to the first law, which I was talking. Where are you? Yeah. So this is your first law of thermodynamics, is it not? Now, depending on the different types of processes, right? Depending on the type of process we can have, right? This particular equation can be modified, right? For example, let us take the thing which we already know. What is an isothermal process? Right? So an isothermal process is one which is going to happen. That process is going to happen at constant temperature. The temperature is not going to change. Okay. Now what is going to happen to this equation? Can I write delta E as N CV del T is equal to Q plus minus P external del V. All things are substituted. Whatever formulas I know, I substitute here. Okay. Now, if it is going to be at constant temperature, can I say delta T is equal to 0? It's not, people, because the temperature is not changing. There is no change in temperature at all, right? So I can directly write Q is equal to minus W, or I can write Q is equal to P external del V. This we can tell. Okay. So if they tell you isothermal process, we have to understand that it is going to be constant temperature process. And at a constant temperature process, delta T is going to be 0. Definitely delta E is going to be 0. So we can write Q is equal to minus W, or you can write Q is equal to plus P external del V. That is also fine for us. Okay. That happens for an isothermal process. Okay. Next one. What happens if I have an isochoric process? Okay. Now, what do you mean by isochoric process? A process which is done under constant volume conditions. Okay. An isochoric process is one where I'm going to have a constant volume process. Right. So if that's the case, I know delta E is equal to Q plus W. Let us substitute the values now. I have NCV del T is equal to Q plus minus P external into del V. Okay. Now it's an isochoric process where I have constant volume. So the delta V is not changing. So I can directly W is equal to 0. So I can directly tell delta E is equal to Q. Right, or Q is equal to NCV del V, whatever it is. Right. So this happens in an isochoric process. All right. Okay. Next is what is my adiabatic process. We have already known what is adiabatic systems. Right. Now we are going to see adiabatic processes. Okay. Right. So in adiabatic process, people, we know that the net heat change is not going to happen. There is no heat getting added. There is no heat loss. So Q is equal to 0, right? Constant heat. There is no heat added. There is no heat lost. Q is 0, right? So if that's the case, delta E is equal to Q plus W, or I can now, since Q is 0, we can write delta E is equal to W. That's it. And W, what will be the formula? Minus P external del V, that you can substitute, get the answer here. Okay. So for isothermal process, you have this equation, Q is equal to minus W. Don't remember anything, people. Do not mug it up. Do not mug up anything. Okay. Go by the logic, right? You know what you have to do. At constant temperature, delta E is going to become 0. So Q will be equal to minus W. Isochoric process means constant volume process. So here the delta V is 0. So W will be 0. So delta E will be equal to Q directly. And adiabatic process, we understand that I'm going to have Q is equal to 0. There is no heat change happening. So you will understand that the delta E is equal to W. Okay, right? So these three are the different equations, manipulations you can do for your different kinds of processes. Okay, right. Now, people, I want to lay my interest upon what happened. Something got stuck. 1 second. Yeah. Again, same issue. Yeah. Okay. Everything came. Right. So now what we'll do is this kind of processes, which I'm telling, obviously isobaric, isochoric, isothermal, adiabatic, all the different kinds of processes. But any of these processes, right? Any of these processes can be divided into two types. One are what are called as reversible processes, and the other one are what are called as irreversible processes. Okay, right. So people, it's not about getting reversed. Okay, please understand that. Right? It is not about getting reversed. It's about how efficiently you're able to reverse the process. Right? Now look into this. Let me give you a similar example. Okay, say there's a stone. Okay, there is a stone. Okay, now this side one guy is pushing. This guy another guy is pushing. Okay, this side one guy is pushing, and on this side another guy is pushing. right? So obviously we know depending on which force is greater, say if it is F1 and F2, if F1 is greater, the ball will move this side. If F2 is greater, the ball will move this side. Is it not? Right. But try to understand a situation where, say, this is 9.999 Newton, and this is 10 Newton. Okay, it's a very small difference between the forces applied on the both sides. Okay, eventually we understand that the overall movement of the stone is going to be towards the left, towards this side, right? But don't you understand that even if I put little more effort by F1, you can understand that you'll be able to reverse it. Okay, right? And also, even if you're not able to reverse it, what you understand is, since there is very less force difference, this ball or this stone will move very slowly. Is it not? This particular ball will try to move very slowly towards the right hand side. Is it not? And it is very easy for us to reverse this process, in the sense that I will be able to make the ball move this side if little amount of more this thing is given to us. Okay, so what you have to understand about a reversible process is that obviously the process is reversible. You will be able to go from one, like say, if at all I have A giving B, I will be able to go for B giving A. But you have to go for B giving A. You can reverse the process with almost no energy spent. Almost no energy spent. Right? If at all you're able to reverse the process without spending much energy, those kind of processes are what are called as reversible processes. Okay, so they should be reversed. That is not the only condition. They should be reversed with minimal efforts. Without almost no effort, you must be able to reverse the process. Okay, those kind of processes are what are called as reversible processes. And all reversible processes are going to be very slow processes. Right, are going to be very slow processes. Okay, right. Now what about irreversible? Exactly opposite. It's not like you will not be able to reverse it. Right, it's not like you'll not be able to reverse it, but for reversing you have to spend a lot of energy. Right, for example, people, right, say I'll give you an irreversible processes. Right, say I have a body at 100 degrees Celsius and I have a body at 25 degrees Celsius. Naturally the heat is going to flow from 100 degrees Celsius to 25 degrees Celsius. Right, but if I want the heat to move from this body to this body, obviously I have to spend a lot of energy. It is not like it's not possible, right? But for me to reverse this, change the direction of heat, you have to maybe supply some pressure, something you have to do. Lot of other things are required for it to reverse the process. Okay, so irreversible process can be reversed with high amount of energy spent. Right, that is why we say it is irreversible. Right, so a reversible process, we should be able to reverse the process with very little amount of efforts. If you are able to do that, then okay, reversible processes. Irreversible processes, you will not be able to reverse them that easily. Very difficult. That's why we say them as irreversible. And all irreversible processes are going to be very fast processes. Right, are going to be very fast processes. Okay, so we can have an isothermal reversible process, isothermal irreversible process, adiabatic reversible process, adiabatic irreversible process. All these things are again possible. Okay, and we will be able to derive equations for this also. And I'll give you more insight. About this reversible irreversible process in the next class. Okay, we will take actual thermodynamic examples and we'll try to understand what exactly is reversible, what exactly is reversible. Okay, reversible, irreversible. We'll get more insight about the next class, and also we'll try to derive some equations for with respect to your first law of thermodynamics. With respect to your delta E is equal to Q plus W. For irreversible process, how it will change. For reversible process, how it will change. We will try to understand that. Okay, right. So with this, I think I can end the class for today. Okay, right. So is there any questions anybody wants to ask me? Okay, fine, people. I'll stop right here. Okay, and we can end the class. Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.